We're going to look at some multiple choice questions on related rates today. These are all AP style. However, I know that one of these 5 questions in particular was not truly an AP question because of the way it is worded. But we'll look at that in a minute. If you need to print the sheet of problems, you can go to bit.ly/rr-mc, and it's a single page PDF with 5 questions on it. So let's get to work on these. Number 1, we have water flowing into a spherical tank with a 6-foot radius, a constant rate of this. So I'm going to stop and make a note to myself. Something is happening at 30 pi cubic feet per hour. That is a rate of change of something. Something, dt, is 30 pi cubic feet per hour. However, they did not tell you explicitly what that is. So we're going to leave that as an unknown. We don't know what dimension is changing at that rate yet. We'll figure it out in a minute. They do tell you that the water is h feet deep. So if you can imagine this, if you want to draw it, we have a spherical tank with a little opening at the top. Water is flowing into that tank and it is filling the tank, and we are finding the volume of a partially filled sphere. Now that is a very bizarre situation. It's not a full sphere, it's like filling it up. And since that is so bizarre, they give you the formula for volume right here. I'm going to copy that down. I am not doing a whole lot as I copy it. However, writing it down again does help me process the problem. Being active is always a smart way to do math. So we have that. There's our volume formula. What is the rate in feet per hour at which the depth of the water, which they describe as h? So I now know my objective. I want to find dh dt when the water is 2 feet deep. So that is a mention of the depth of the water. So when h is 2 feet, and anytime I'm given a direct measurement of something, I always ask myself, is that constant or is it changing? And that is definitely changing. So I want to make sure I hold off. I will not plug in 2 until after I find a derivative. And now back to the 30 pi feet cubed per hour. They didn't tell you what that was. They just said the water is going in at that rate. But it could be the radius, because they mentioned radius right here. They do say that this tank has a 6-foot radius. I guess I could draw that in. It doesn't really come into play. We have a mention of the depth of the water, and we have a mention of volume. They don't tell you that this is volume. However, the units should, because we are looking at something that changes in feet cubed. That is how you measure volume. So that is dV dt. Now we have everything, and we are ready to start the problem. And with related rates, we typically just jump into the derivative, but you shouldn't. You should always stop and think for a second. Can I make the derivative any easier before, with algebra, before I start the derivative? In this case, you absolutely can. As the problem is currently written, we have a product rule. We have pi h squared over 3 times 18 minus h. However, if I distribute, I will get rid of that product and we will have a power rule. And I am only going to distribute the h squared. The pi over 3 is a constant. I can leave that out. However, if I distribute that h squared, I now have an adjusted formula for volume that is pi over 3 times 18h squared minus h cubed. And we have a nice clean derivative now, no more products. So when I jump into the derivative, dv dt is going to be pi over 3. That's a constant. I'm just going to leave that pi over 3 out here. It doesn't go anywhere, but it doesn't bother me. The derivative of 18h squared is 36h dh dt. Don't forget that implicit part. Minus the derivative of h cubed is 3h squared dh dt. And now we plug everything in. We are solving for dh dt. I need to plug in 2 for h, and I need to plug in 30 pi for my volume. So I'll do that. So I have 30 pi equals pi over 3 times, I'm plugging in 2 for h, 36 times 2. dh dt is what I'm trying to find. I'll leave that alone. Minus 3 times 2 squared dh dt. And now we do a bunch of arithmetic and algebra to solve for dh dt. Since that is algebra, I'm going to pause the video while I do this, and in about 2 seconds, you will see the answer. And there it is. So I multiplied by 3 over pi first, combine the like terms, divide by 60, and you get 1.5. Well, I got 3 over 2, but multiple choice, got to go with the decimal, I guess. All right, number 2. these are the more straightforward and, dare I say, nicer related rates because everything is usually explicitly given to you in problems like this. So we have our formula, y equals 2e to the cosine x. Again, I am not really doing a whole lot of glorious math here, but rewriting the problem does help you process it. X and y are varying with time. Y increases at a constant rate. There's some good information. dy dt. And if y is increasing, it will have a positive derivative, and it is units per second. The rate in units per second at which x changes when x equals pi over 2. So x equals pi over 2, and they do tell you x is changing, so I'm not doing anything with that yet, is what? So we're trying to find dx dt. And here's my formula. I'm trying to think of ways I can make this derivative easier, and I cannot think of any, so I'm going to go on with the derivative. dy dt is going to be the derivative of 2e to the cosine x. I'm not going to worry about that 2. Derivative of e to the cosine x is e to the cosine x times the derivative of cosine x, which is negative sine x. And I like to stick that in front of the exponential function. Now, don't forget that I almost forgot this. We need to multiply by dx dt as well, because I did do the derivative of an x term. However, we are differentiating with respect to x. And as I almost illustrated, it's easy to forget that when you're doing problems like this because it just looks like a normal function that we've been doing derivatives of for about a month now. But we are differentiating with respect to t, so don't forget that dx dt. And I would have realized that eventually because I'm trying to find dx dt. So I would have realized that it's missing in my problem at some point. Now I start substituting everything I know. I know that dy dt is 5. So 5 is equal to, I'm going to say that's negative 2. I'm going to take that negative out here. And then the sine of pi over 2 times e to the cosine of pi over 2 times dx dt. And once again, we are now at a point where we can solve this with algebra, and I will pause and show you the answer in a second. And there we have it. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And it cleans up quite nicely. And once again, we have to go with decimals. So there is number 2. Let's look at number 3. And 3, I believe, is the worst one, or I'll say the most challenging problem on this sheet. So we have sand being dumped on a pile in such a way that it always forms a cone. The base radius is always 3 times the height. So I'm going to make note of that. The radius is always 3 times its height. So I can write that down. Radius is 3 times height. We have a function v for the volume of the cone, and we have a graph showing different values of v at different intervals of time. Let's see, we are measuring in cubic feet per minute. At what rate in feet per minute is the radius of the base changing? So my goal is to find dr dt. And we are looking when t is equal to 6. Okay, that's interesting. They gave me a unit of time. Usually on these problems, they say when the radius is 4 or something like that. So we're going to have to somehow factor in t equaling 6. And what I did not give you in this one is the formula for the volume of a cone, which is typically provided in the world of AP calculus. So the volume of a cone is 1/3 pi r squared h. And now we have to process this problem and see what we can do with it. And I'm looking at it, we usually jump into the derivative, and we could jump into the derivative. However, the derivative is going to be really ugly. Let's look and see what happens with the derivative. Okay, so here's our derivative as it's written. I wouldn't write this down yet because I'm about to erase it. We do have a product rule with r squared h. So, and I messed that up. This should be 2r dr times h. Okay, so we have a product rule with r squared h. And what we will run into if we go this route, and we can finish the problem with this information. It's going to be a chore, but we run into a lot of unknowns. I don't have dv/dt at the moment. I do have, no, I don't. I don't have R. I'm looking for dr, so that's okay. I don't have H. I still don't have R. And I don't have, like, we have a lot of unknowns. And there's going to be a lot of unknowns either way. However, with this problem, I have R's, DR's, H's, DH's, and DV's. That's 5 different unknowns. And if you can cut down on the number of unknowns in a problem, it will be significantly easier. And in this case, we can. We can because of this relationship they mentioned at the very beginning, R is equal to 3H. Well, if R is equal to 3H, and that is always the case, this is not some instantaneous relationship. This is always the case throughout this cone of sand piling up. That means I can take this relationship and I can substitute 3H in for R, or I could substitute a different way. I could solve for H and plug in R over 3 for the H. And so let's look at what we get when we make those two substitutions. So here's what we can have if we make these substitutions. I can either plug in the 3H for the R, and if I do, I end up with a volume formula of 3 pi H cubed, or I could solve for H. H is 1/3 R, and if I plug that in for my H, I ultimately end up with volume being 1/9 pi R cubed. Both of these volume formulas are significantly easier to differentiate than the original. We don't have a product rule anymore. It's just an H cubed or an R cubed. Very easy derivative. Now, which one do you want to go with? On the surface, you may say V equals 3 pi H cubed. However, you need to be aware that we are trying to find dr dt. And since we are trying to find dr dt, we need to keep r's in the equation, which means we need to use volume equals 1/9 pi r cubed. So while the H one was cleaner, it didn't have the fraction 1/9 in it, we're going to go with this one over here. So I'm going to bring it over here. Change its color to blue so it matches the rest, and then we will be ready to differentiate. Let's see, I'm going to get rid of this green stuff here because that is not what I did. Come on. There we go. All right. So now I am ready to differentiate and hopefully solve this problem. So my derivative of volume will be dv dt equals, I'm going to ignore the 1/9 pi. Derivative of r cubed is 3r squared dr dt. And now we run into a second problem. I need to plug in for dv dt and I need to plug in for r. Because I'm solving for dr dt, I don't have either one of those things yet. This is where the graph is going to come into play. And at time t equals 6, I am right here. And what I know is that my volume at time 6 is 4 pi. I can see that on the graph. And I know that my volume is equal to 1/9 pi r cubed. I can use that to find r. So I'm going to find r really quickly. There we go. R is the cube root of 36, which is really ugly. Now, you can look at the answer choices and tell that we punched this in a calculator at some point. I'm going to leave it as cube root of 36 now, and I can substitute that in down here. But then we're going to run into another problem because I don't have dv dt. I need to figure out what dv dt is, and that's another task here. So how am I going to get dv dt when time is 6? Well, dv dt when time is 6, I could rewrite that in a different notation. That is v prime of 6. And if I'm looking at the graph of v prime of 6 would be the same as the slope of the tangent when t is equal to 6. So I'm going to drag that. So here is the tangent when t is 6. And we have to estimate, we have to figure out about what that slope is. And we can do that because it looks to me like it's a rise of 1. If I draw this in from this point to that point, it looks like I'm going up 1 over 1. So you may think that's approximately 1, and it would be an approximation. However, look at your units. If I go up 1 unit, I go from 3 pi to 4 pi. So that's actually an increase of pi and a run of 1. So dv dt is going to be approximately pi. Now I can plug in cube root of 36 and pi for my r and dv dt. And when I substitute those in, I will throw this in a calculator. 3 times the cube root of 36, holy cow, that's ugly, squared dr dt. We will solve that in a calculator, or I'll divide that in a calculator and get my decimal answer. All right, there we go. So I'm getting 0.275 when I solve that. That is a very challenging problem. This is the one problem I was referencing at the very beginning that when I said one problem is not worded like it would be on the AP exam. This one has 2 instances. On the AP exam, they typically give you the formula for the volume of a cone. So the fact that that was not provided tells me I pulled this problem from some supplemental material that's not College Board. Also, on the AP exam, They will ask you to look at a graph and determine if the slope is positive or negative. However, they won't expect you to estimate a numeric slope the way this one did. So we had to estimate the slope to be approximately pi. They don't do that on the AP exam. They do very frequently give you a graph and they'll give you a function. They'll say, is the derivative positive? Is the derivative negative? And they'll ask big picture questions like that with estimations, but they won't ask you to, or they have yet to see them ask you for very specific slopes like this one did. Anyway, so let's go on. The next two are a little bit nicer, I believe. So number 4, we are looking at a square. The area is expanding. The square is expanding and the area is increasing twice as fast as its side length is increasing in linear units. So we have a square. Our side length, I'm just going to call x. The area, where it talks about area, so the area would be x squared. And it tells you that the area is expanding twice, the area is increasing 3 times as fast as its side length is. So with the area, dA dt is increasing. So I'm starting with this area is increasing 3 times. So 3 times something, and it is increasing 3 times as fast as its side is increasing. So I have my side length written as as x. So it'll be 3 dx dt. My multiplication dot looks like a subtraction sign. There, that's better. So dA dt is 3 dx dt. And now we're trying to find the side length. In this case, they didn't give you when the side length is 4 or when the area is 12 or anything like that. Would have made this a heck of a lot easier. So they gave me a mention of derivatives, however. So let's find the derivative. D dt of that whole thing. So the derivative of area would just be dA dt. dA dt is the derivative of x squared is 2x dx dt. And now I need to start substituting, and I'm simply going to substitute 3 dx dt for the dA dt, and this will fall into place quite nicely. So 3 dx dt is 2x dx dt. And the question is asking you to find its side length, and I probably should have written this down. The side is what? So my goal is to find x, as I've called it. I didn't want to use s because it looks too much like a 5 to me. And when you start dividing this, the dx dt's actually divide out, and you will get 3 divided by 2 is x, which is option B. So considerably easier than number 3 was. And let's move on and finish up with number 5. The edge of a cube is increasing at 0.2 inches per second. So again, we're looking at, well, it's not a square, it's a cube, square-ish, all right? So we have a cube. Wow, that was crappy. Look at that cube. Okay. So we are looking at a cube. The edge is increasing. So that is dx dt. The edge length is increasing at 0.2 inches per second, and I may end up converting that to fractions. At the instant when the total surface area is 150 square inches. So when the total surface area is 150 inches squared, what is the rate of increase in cubic inches per second of the volume? So I'm trying to find dV dt. So they mention 2 measurements of this cube. They mentioned surface area and they mentioned volume. Since I'm looking for the change in volume, I'm going to start with that. And you should know that the volume of a cube is x cubed. And I can't really clean that up. I'm not going to be able to make any substitution. So I'm going to go ahead and find the derivative. dV dt would be 3x squared dx dt. And I am trying to find dV dt. So that's my objective. That's going to remain dV dt, which means I want to substitute for x and dx dt. I do not yet have a value of x. dx dt is 2/10. I'm gonna go ahead and change that to 1/5. I just like fractions better. They're easier to work with in my opinion. So that's 1/5 inches per second. Now to find x, we typically, and I've said this before, we typically go back to your original formula, volume is x cubed, and substitute something to find x. However, in this case, we can't do that. And we are going to use the fact that we know the surface area is 150 and the surface area of a cube, well, each side is a square and there are 6 squares and each one is x by x. So your surface area, I'll just do A, is the area of one of those faces times 6, so 6x squared. Almost, in my mind, I was about to find the derivative of this, but I don't need to find the derivative of this. I need to solve for x when A is 150. So 150 is equal to 6x squared, and then we will solve that for x. You will get 5 for x, so now I can get rid of that, replace it with a 5, and that cleans up quite nicely. dv dt is going to end up equaling just 3. And what the heck did I do wrong? I forgot my exponent of 2. Well, it's a good thing they don't have 3 as an answer. All right, so this is 3 times 5 squared, not 3 times 5, which changes this to 15, which is one of the answers. Haha. So there we go. There are 5 related rates multiple choice questions for you.